Hey there, this is Arna from Pebble, and welcome back to the Introduction to Linear Algebra series. And I would say that this video is the halfway point of the entire course. And so we only have a bit left in Chapter 3 before we can move on to Chapter 4 with the eigenvalues. So this is your midway point. Congratulations on making it this far. And in this video, we're going to talk about change of basis. So we're going to dive into what exactly change of basis is. And so let's say that we have some vector. Okay, so like v of vs is our vector, and that's something like 7 2, and this is with respect to basis c. And so c is going to be our standard basis. That's 1 0 and then 0 1 for the set of all real n tuples. And so what if we did this with respect to another basis, like a substandard basis? Okay, so what if I said that we did 1 1, a non-standard basis value, and then we also did 1 minus 1. And so what if we did this instead? What would you make this out to be? Well, you would find that the coordinate representation for this specific vector is VD, and that's going to equal 9 by 2, 5 by 2 with respect to our basis D. So these two are two coordinate representations for the same vector. So if they're representing the same vector, well then there must be some mathematical correlation between the two that we can represent. Okay, so we want to ask this question, whether our different coordinate representations for the same vector are related. Okay, and so the way we define our vector is by a set of linear combinations of the bases. So for C, we could say that C1U1 plus C2U2 all the way up to CNUN. And then for D, if you were to say for D, that would be D1U1 plus D2U2 plus all the way to DNUN. So this would be just decomposing that in terms of our basis, right? So there exists this unique set of scalars, right? So that basically just means that since each basis vector in C is also a vector in V, it too can be expressed as a unique linear combination of the basis vectors in D, basically. So we're gonna be trying to represent the basis of one representation in terms of the basis of the other representation, because by definition we should be able to get that and it should be included. Okay, so let's say that we have something like u1, right? This is our basis in either C or whatever, and so that's going to become, let's say we have P21 B2 plus all the way to Pn1 Bn, and then we also have another vector here, P12 V1 plus P22 V2 plus all the way up to Pn2 and 2Vn. And so for any scalars, basically, you're gonna say that our vector for that is gonna be equal to P1j B1 plus P2j B2 all the way up to Pnj Bn, basically. So if you use the n tuples that are generated by this, So each corresponding. This one corresponds to these as are scalars that belong in the n tuple, right, for the coordinate representation. So if you were to use all those n tuples as part of the columns for some matrix, let's say P DC, well then, so we're saying respect to both these bases. Well then, what we can do is we could say P11, P21, all the way up to Pn1, and then you're going to get P12, P22, and that's going to get you to Pn2, and you're going to get P1j here. So just writing out this matrix in just a simpler format. You can go with, if you have constraints, this will obviously be smaller, but because we're trying to make this for any size vector, you just gotta write it like this. These dots. So we're just saying that it goes all the way up to in both directions, basically where that value is going to equal n. So this is indeed square. So this is our matrix P. Okay, so we're mapping from the C basis to the D basis because we go from bottom to top. And this is what we call a transition matrix. So basically what this is this is going to change, or it's going to transition from the C basis to the D basis. Okay? And so if you take a vector, some vector in the C basis, let's say something like BC, well, if we multiply that by what we got here, PDC, that is going to give us the output of the same vector, but in coordinate representation in terms of the basis D. And so that's the main beauty of vectors in linear algebra, is that we can mathematically relate them. They're the same vector, just represented differently. So what we can do is, well, we could take the representations of the bases. So we can map our bases as a linear combination of our starting point. So we're taking all the matrices, all the bases vectors in D, and we're just expressing that as a linear combination of the basis of C. And that is going to provide us with a mapping. That's going to tell us, well, how much of what. And so we can use that inside our matrix to get this big idea here, our transition matrix having transitioning our thing here. Okay, and so this brings us to a theorem that says basically if VD, VC, and VD are the n-tuple representations of some vector V with respect to our bases C and D respectively, and if Pj is the n-tuple representation of the jth basis vector in C, so basically just the vector base, the basis vectors, with respect to the D basis, well then VD is going to equal P of C to D VC, where the jth column of PC to D is Pj. Okay, so that's basically just what I said in theorem form. Okay? And so the subscript superscript notation is really helpful in tracking which transition matrix can multiply with which coordinate representation. Because note here that we're saying PC to D, bottom to top. So we can't do something like VC equals P C to D of VD, because this is gonna map the wrong vector to the D basis. So this is gonna pretend that this is a vector inside our C basis and map it into our D basis. Again, well, it's already in D basis and we wanted to get into C basis. So what you need to do then is you need to find the transition matrix for PD to C instead. Okay, so it's kind of like finding the operation that will do the process that you want it to, and you need to find that matrix. Okay, and so, these matches, okay, so this match and this match, these two need to match in order for our value to actually be truthful. And so one thing you'll note is that the transition matrix EDC is gonna be the inverse of the transition matrix P C to D. So inverse of that, these two are going to be mathematical, or these are going to be matrix inverses, and that's something that's very good to note. Okay, and so that brings us to a theorem. The transition matrix from C to D, where both C and D are bases for the same finite dimensional vector space, it's going to be it's going to be invertible, and its inverse is coincidentally going to be the transition matrix from D to C. And that is something you can do instead of, that gives you another option. Instead of finding the transition matrix again, you can just take the inverse, which is something very, very cool. And I'm going to leave the proof up to you. I want you to try it. And it's a very, very cool proof. Okay? So let's find the matrix representation for the linear transformation again. Actually, no, sorry. That's not what I want to do yet. Okay, so one thing I want you to know is with linear transformations, the matrix that you're going to get when you make the representation, so the matrix representations that we learned in the past two videos, those are going to be basis dependent. So if you change your basis for either the input or the output, well, then your matrix is going to change. Okay, and so let's take something, let's take a non-standard basis for the transformation T. A, B. Let's do something like 11A plus 3B, and then minus 5A minus 5B. And so if you take this as your transformation, right? Well, if we take a non-standard basis, like E11, well, then what's that going to give you? Well, that's going to give you 212, I believe. Will it give you 212? Yeah, okay, it'll give you 212. And then if you take the other matrix here, the other vector in our basis, well then you will get 4, 4 in terms of our basis D, which is these two vectors here. And so as you can see, this is different than what you might expect from just first glance. Okay, so this is mapping D to D. So this is A D to D. And so for the standard basis, what you'll actually get is 11.3 minus 5 minus 5, right? Because that just makes sense based on our values here. So this would be for a standard basis. If it was something like C, standard basis, this would be a linear transformation matrix representation. But for a non-standard basis, you can see how it's changed, right? And that's where change of basis. You can also see that, well, are different matrices that represent the same linear transformation, are they related, right? And so that might make you think. So if you have, well, something like WC, which is the output of your transformation, and then you have something like A, C, C, B, C, and then you also have WD equals A, D, D, BD. And so these two, well, VC and VD are going to be your n-tuple representations for the same vector V, but with respect to different bases. Then you're going to say that there exists some transition matrix that's going to say, well, VD, that's going to equal P, C, D, C to D, B, C, right? And then that is gonna consequently tell us that, well, WD is gonna equal P, DC, WC, right? So for these two. And now let's apply this to our previous equations. So WD equals AD DVD equals ADD PDCVC. And that looks confusing. And it is confusing. But yeah, the PDVC is going to equal PDC ECCVC. Okay. And so basically by plugging in this into our equations here, that what we're going to understand is ECD ACC BC equals AD ADD ADD PCD BC, and that's gonna, well, say that it's valid, that these are equal, right? And so that's equal for all vectors with respect to the C basis. And so if we take VC to be a vector having 1 as the first component with all of the components equal to 0, then the vector having 1 in its second component with all of the components equal to 0, and so on through the entire standard basis, well, then what we're going to get if we apply that logic is, well, PDC equals ACC. So basically just canceling out the VCs. That's going to equal ADD PDC. And, well, the transition matrix is going to be invertible. So let's try and find ACC. ACC equals PDC inverted plus ADD EDC. And so if this is going to be valid, right, then A, C to C, and D, A, D to D are matrix representations for the same linear transformation with respect to the C and D basis, respectively, where these two bases are related by the transition matrix P, C to D. If we simplify our notation by omitting the subscripts and superscripts and using different letters to distinguish the different matrices, well, you're going to get A equals P inverse BP. Okay, so two n by n matrices A and B represent the same linear transformation if and only if there exists an invertible matrix such that A equals P inverse BP. Okay? And that's the main gist here. And this is an equation for what we call similarity in linear algebra. And so we're going to say that two matrices are similar if they represent the same linear transformation, which means that, well, if you have some vector B and if you have a matrix A, some matrix B, then there has to, if they're similar, then there's going to be some matrix P that can do this. So PA equals PB basically. Two matrices are similar if the same matrix multiplied by them equals the same matrix, pretty much. Okay, so that concludes change of basis. That's the main ideas that you need to know. And there weren't many examples in this lecture, but it's mostly just applying the techniques that we just went over to solve problems like finding matrix representations and change of bases. Anyways, I'll see you in the next video.